vast difference in the outcomes. And yes, the system is governed by specific rules, but the outcome can be appear random and unpredictable. And our non-linear, our chaotic system will produce feedback loop, and this feedback will cause the system state to influence itself in a complex way. So in each parameter, each state variable will be involved towards this. And also we have the boundedness. Even it is appeared random and unpredictable, but then it's still confined in the same attractor. And the key component to understand how system transition from stability to chaos, we already discussed the fixed point and the stability and everything. Also bifurcation, limit cycle, component of exponent, fractal, and also invariant measure. So it's all still fresh with you. So let's recap that we have learned the Lorentz equation. So we have two nonlinear terms whereby xy and xz. So this is nonlinear that make the system chaos. And using this value of parameter, sigma is 10, rho is 28, and beta is 8/3. The system will exhibit chaos. Okay? So now we want to solve this system using Rajkutta, and I will choose the time step is 0.01. And I already mentioned why we need the small time step. Why we need the small time step? Smallest better. So I already mentioned in the previous lecture. So why do we need the small time step?
Better approximation.
Yes, better approximation. Accuracy is also very good. Okay. So maybe I remove first. Sorry. I don't want to show my code actually. I want you to do first. So because this is what you have to try. So let I remove first few things. Okay? Or maybe you can also try directly how to plot 50. I mean how to solve the Lorentz. Okay, so let's try how we want to solve this equation. So at first step you input this parameter, okay, sigma, rho, beta with this initial condition. So this is the initial setup. So try. I also will check my MATLAB. Okay. So you are giving the parameter and then the initial condition, and also you put the time step. Maybe you can iterate it to 50 by using 0.01 or maybe 100 also, okay? Iterate until 100, and then you put it this equation, and then you put it this equation, and then try to solve using Rajkota. Okay, so try write sigma equal to 10 in your MATLAB. Sigma equal to 10, and then semicolon, and then the next one is row. You can spell sigma row.
Hello.
Yeah, we got it already. Whenever you need to use the option. Yeah, it's okay. Your time set is yeah, it actually doesn't matter how you want to, how long you want to activate. So put it in initial condition. Put the initial condition. Okay, so for this is for plotting the phase space, and I think also for the time series. I think also for the time series. So I have the time series also. The for this one. And the phase space I didn't show yet. So basically this is the way how we want to plot kinetic system. So we have the parameter, and then we put it in initial condition and our time step, and then we input our function into this one. So my function's name Lorentz equation. So this is the equation, and then we solve using Rajkota. So Rajkota here is actually ODE 45. So we use this function because we have the time span and the initial condition. So they will start from the initial condition to run it. And this one, I would say I would like for you to have the time series first. That's why here I plotted the time series. So So the plotting, the display names, is just a makeup for that, our legend and everything. no pattern at all. So as you can see, the amplitude of each time series is not the same, and in fact the frequency also will be not the same for each one. So and then sometimes there is a fluctuation, and then it come also the fluctuation again. So means that it is in chaotic behavior. So if you can see the time series is does not any manner, it's not any pattern. So we can see it is in chaotic state. Okay. So and then you can try to change the initial condition. Also you can try to change the parameter, and then you can see what is happening to your time series. So if you change the parameter, as you know, in chaos, in Lorentz, what parameter is very important to check the stability? Rho. So when rho is 28, that's why you get chaos. So now try to input your rho is maybe 5, and then you can see what happens. Maybe 1. So yeah, so maybe because I don't have that one, so maybe I will try also to share. So maybe I try with 5. So you see? So you see? This is when my rho is 5. And this is the time series. So you see? This one is converging. It's a stable one. And also the phase phase is only a spiral like this. So you see the difference between these two? So you can, that's why when we have the system, it's very tedious to get what parameter that chaos will be. So there is the major part in chaos theory. Whenever you have the system, you want to check, you want to analyze what parameter that the system will exhibit chaos. Okay? So you can try with others. Okay, wait, maybe I just use PowerPoint. So easy to. plot to see the beautiful of chaos. So for row just now, what is the rules of row in Lorentz system? What is the rules of row? Yeah, you know, right? The row is very important. So when you change just now, row to 5, the system is actually stable. So what is the rule? The rule of row.
Should be greater than equal to 20.
So it determines the stability. So it determines the stability of Lorentz. Okay, so of Lorentz. So if we have row less than 1, so the trajectory will be converged to the origin. And if you have row greater than 1, it will be exhibit periodic and soon it will be chaos. Okay, so I would say we move to the second part, whereby oh, okay. So here I'm giving okay. So here I'm giving you short notes of the changing parameter, also changing the state variables. So when we increase the row, what will happen? When we decrease the row, what will happen? And also for sigma, also for beta. So also if I slightly changing the initial conditions, so what will happen? So let's see, we check if we increase the row, so it will be more dense. You can check through your through your MATLAB. You go for, let's see, row is 50. So you can see the butterfly there will be more dense, means that it will be more chaos. And if you change your row into, for example, like less than 24, this is our hallmark, right? So let's say like 10. Oh, sorry. Yeah, like 10. So it will be like periodic. You see, it will be like periodic, and the fixed point behavior over there, so it will be stable. And try to check if you change your sigma, you increase greater than 10 or you decrease lower than 10. So you can see it will be different behavior will be happening. Okay. So I'm giving you the, a note for different value of parameter. Okay. So in the next, I want you to do for stability. Okay, stability analysis. So for the stability analysis, what we are looking for is eigenvalues. Okay, so before we get the eigenvalues, we need to find the fixed point. Okay, so do you remember the fixed point just now that we did in the class? So we have two fixed points. One is the trivial fixed point and one is non-trivial. Okay, so now we input the parameter. We put the fixed point calculation. It's not fixed point calculation. It's actually we need to plot to give the fixed point itself, and then the Jacobian matrix. Okay, and then we compute the eigenvalues, and then we can get the result. Okay, now try.
Please show us that code for 3D trajectory. We have not.
Oh, okay. Oh, sorry. Okay, this one. This one.
Yes, ma'am.
Okay, yes. Please.
You can also share this. I can share it. No, share it.
Okay. directly say, no, 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 this is not chaos. So, no, you plot time series, he said. And then I'm so confident that time, I plot the time series. And then he laughing at me. You see? So that's why even you see the face is like condensed, it doesn't mean it's still chaos. So that's why you need to check the time series, how the fluctuation, how the amplitude, the frequency of it. Okay? And then that's why I'm started with the time series. Okay? And then you can go for the 3D plot. So this is what we call phase space. Okay. So then, okay, now I'm moving to the stability, right? Okay. I have the code below here, but maybe someone can try. Of course we want to check your ability first before we show everything, right? So anyone know how to find the stability? I mean, it's just to find the eigenvalues using MATLAB. It's just a matter of using, find the fixed point. Sorry, find the eigenvalues using MATLAB. Anyone there? Yeah.
So you can show the matrix, not the code.
It's okay. It's just actually because we have 2 hours, so
We need to remember the matrix.
Yeah, it's okay.
Eigenvalue is easy.
let me make it bigger. Okay, so first, our parameter. Maybe you can use in other worksheet. Okay, so this is for stability analysis. So we input the parameter, and then we have the fixed point. As I mentioned just now, it's not a calculation, it's a fixed point. That's why in the lecture just now, I'm giving you how we want to find the fixed point. So fixed point itself is not a calculation, so you need to write your fixed point. So this is our trivial fixed point, and then this one is our non-trivial fixed point. Okay, so as you can see, our square root beta times rho minus 1 just now. So this is what we input, and we have 2 positive and negative, so that's why we have P plus and P minus. Okay, so this is for fixed point calculation. And then the second important thing is your Jacobian matrix. So this one is derivative of each particular partial derivative xyz, and also you have to input this one. Okay, and then for eigenvalues, you want to check the fixed point. For this one is for the first fixed point. You compute the eigenvalues for for trivial fixed point. This one is actually easy, and then this one will be the same. One for the positive one, one is for negative one. And then you can display the result, and then you can check the output. Okay, so maybe I can share the one that I have done, so we can see the result. Jacobian. So the information Jacobian provide is only about the stability. Okay, so they give the information of the stability. Okay, so if you can see our result, this one I'm using, of course, I'm using the parameter whereby the system exhibit chaos. So okay, as you can see, when fixed point is 0, so you have two negative part and one positive part. So this is indicate what? We have two positive two negative and one positive. It means two negative means it will be stable. Okay, and then the positive part will be unstable. Okay, and then when we find the fixed point for the non-trivial part, we get the eigenvalues of positive and eigenvalues of negative. Okay, so here also you can see one is negative part. So negative part is stable, and these two is complex. One with both are positive. Okay, both are positive. So for the minus also we have one negative and two complex number with positive real part. Okay, so that's why it is unstable and is a chaos. So now we try. I don't know whether you managed to write this one or not, so that's why I'm showing this one. So let's say we are changing the row. So let's see the value of fixed point, and then you tell me what is the analysis of it. Is it okay? I'm providing you the code, so you are telling me what, because we already discussed. So what is the result, the analysis of it? So let's say we change the row to 5. Okay. So when we run, of course we will have 0, 0, 0. Will be the same. And two negative real number and one positive. And then we have non-trivial. Also we have negative number. And this one is negative. Right? You see the difference? You see the difference? So in this parameter, rho equal to 5, our complex eigenvalues is negative. What does that mean? By our previous lecture, the system is stable. Okay? Okay? So that's why after we are plotting, before we are so confirmed, so we have to check the stability. Okay, so the stability will mention us the behavior nearby the fixed point. Okay. So are you okay with this? Okay with the fixed point? With the eigenvalues is positive. Okay, so why the trajectories nearby P positive and P negative shows oscillation between oscillation. This is the oscillation behavior before it diverge. You see the divergence here. This one we not really see it. So why the trajectories nearby the fixed point oscillation? Also the same. It's just because of the eigenvalue. Okay, so nearby the fixed point, the trajectories oscillate because the complex eigenvalues. Okay, and already now we already checked for this one. What will happen if rho less than 24? So we already checked that one through the phase space and also the time series. We can see it is very stable. Okay, so now let's move to Lyapunov exponent. Okay. So this one I'm using so this is the Lyapunov exponent. Okay, let's go line by line actually. Before we, it's too small, right? Okay. So this is actually I'm using the trajectory method, where the trajectory method is actually we are finding the difference between point point X, for example, in one initial condition, and we perturb it for the second initial condition, and we check the difference of the difference between these 2 points. Okay. So again, because for now we should know already the rho plays important roles in terms of stability. So whenever you have the system, that's what you have to check. So what parameter actually will affect the other system? So for Lorentz equation, so rho is play importance in terms of the stability. You can see from the stability analysis just now, and that's why we vary rho. It's up to you. So in my code, I vary rho from 0 to 50. Okay, and then this is my simulation setting, whereby the time span is 0.01, the time step, and I have the first initial condition 1, 1.6, and the perturbation is actually very small, 6 decimal places difference only between these two. Okay, it's very small, and then we store the Lyapunov exponent. Okay, and then what we do is actually we loop the parameter value of rho. Okay, so and then we need to define what system that we are using, and then of course we need to solve for it, and because we have 2 just now, the initial condition, why we initial condition 1 and 1, and the other one with the perturbation. Okay, so and then we can calculate the separation. Okay, so this calculation is very important for us to find the to get the Lyapunov exponent. Okay, so first we check the distance, and then we find the logarithmic the log growth, and then we find the average of the growth. What?
Skip it.
Okay, you want to skip already. Okay, and then we can rotate, right? Our trajectories can rotate, can grow, and then can shrink. So it's like unstable. So that's why tangent vectors is very important to make sure our numerical accuracy. Okay. So that's why we are using the orthogonal tangent vectors. Okay. So now let's move to the next. Do you want to write it? I mean, I don't want to share the slide, of course. So I don't know how should we do?
No, sharing the slide might be better because then only they can do. And obviously we need to submit to them as well to
Also for the tutorial?
tutorial.
I see.
No, if we share in the earlier, maybe they don't do, they just copy paste. Maybe you can share
but then this
after
is what
that.
in the figure.
Yeah. Maybe you can share after that also, it is okay.
Oh, okay. Okay, so bifurcation. So now we talk about bifurcation. Okay, so for bifurcation, of course, we have our parameters, and then we set up our system, and then we loop the bifurcation process, and we solve it, and then we extract the values of the all the coordinates. Okay, and then we store the row and also the corresponding values. Okay, so and then we can plot the bifurcation diagram. I have the next one, but then I have few questions to be asked here. So what happens if sigma or beta is changed? I mean, what will happen if we change the value of sigma or beta? Just now we try already to plot, right? When changing of sigma and beta. So in bifurcation diagram, what will happen? Let's see the result. I mean it will be the same result as previously. I think this one, right? Yeah, this one. Okay, so it will be actually the same result. So if we increase, the attractor will be stretched in the faster transition. If we lower the sigma, it will be compress the attractor, but then with slower transition. And because beta is our geometric factor, so it will be stronger damping. Okay, attractor will be more compressed, and if we less the beta, it will be weaker damping, and also, but then the oscillation will be larger. Okay, and then here we actually remove. Wait, I not remove. My question is why is it important to let the transient die out before analyzing the steady state behavior? Okay, this part is where no, I didn't see. I didn't see for Lawrence. I didn't do this. Actually sometimes in, for example, in Rosler, we need to remove the first of 200 early transient because we want to analyze because it just represents the temporary dynamics, so it didn't reflect the behavior, so that's why we remove that part. But then I think in this particular code I didn't remove, maybe because Lawrence doesn't, I mean not that doesn't care, what we call it doesn't bother, because in any result it will be dynamics. I mean we can check the dynamics of long-term behavior. Okay? So yes, I see you raise. Yeah.
Okay.
Yeah. Okay. Yeah. Okay. So this is bifurcation. Let's see the result. Let's see the result. Okay. So this is the result of bifurcation. So what do the points in the diagram represent? So you see how the dense point here, and yeah, this one you know is already is a standard. Yeah.
Is it important to like remove this, like why you're removing this interval for the transient effect? What happened if you didn't do that?
Yeah, that's good question. Because if I, for example, in Lawrence nothing happen. In Lawrence doesn't happen. But then in Rosler, if you are not remove the transient, you didn't get the bifurcation. So sometimes it actually depends on how you model your
how
system.
we come to know in the case of new system, like you have to remove transient or not?
No, we don't know. So you have to check.
So is it compulsory to always remove it?
Better that way. So because basically for the first 100, it just showing the temporary behavior. So because when we want to plot bifurcation, we want to check the long-term behavior. So at the first moment, it doesn't. That's why I didn't get the word. It's not doesn't care, but then it doesn't bother too much.
But ma'am, in cryptography we use random like numbers.
Yes, correct.
And in starting they don't behave like that. So that's why you're removing for the transient effect, right?
So
like when we used it in the cryptography.
yeah. So when we use in cryptography, let's see in my case, there is some. It depends on how you want to design actually. So for my case, there is some that I develop. I'm using for the starting. I mean, I take all the result from the start. But then there is some that I remove the first. I mean, the first 100 parts. It depends on the way you want to design. But then, yes, if you are using, for example, if you are using Lorentz for your cryptography, and if you are using exactly the parameters and initial condition like 111, so it's very unsecure because you know that is very common. So better to choose other initial condition. So it's very difficult for us to, I mean not for us, for the cryptanalysis to be done. So whenever you're not using the initial condition as 111, for example, then there will be no issue for you to use the first solution. Okay? Okay, so actually, so my question is, what is the point in the diagram represent? So I just mentioned just now, it represents the steady state behavior for the steady state
It gives the interval where the chaos happens.
Okay, that is good. Yes. It denotes us where the chaotic behavior and stable behavior. Okay, one point. Anything else? So actually bifurcation also indicates the small changes in parameter, which the parameter drastically alter the result or the system behavior. So that is also one thing for bifurcation. Okay, so basically, yeah, because bifurcation, I would like to emphasize because I also have a kind of problem to code bifurcation in MATLAB. It's not that easy. Of course, Lawrence would be very easy for me, but then for other system, for new system, because sometimes we have to make up a few things here to get our result, because we know already from the stability analysis, we get from the Lyapunov exponent, and we already checked their analysis, so we just need to plot the bifurcation diagram. And so sometimes there is sometimes that I didn't get the plot that we want, which is predict doubling, the dance of bifurcation diagram. Yeah, but then there is something quite difficult to plot, especially when you encounter with a new model. Okay, so that's all for Lawrence. So to recap, the first things that you need to know is for sure you have the system. After you have the system, you need to check for each value of parameters. Okay, and then you do your time series. After you do the time series, you can plot your phase space in 3D. And then that is not enough. You need to check your analysis in terms of the stability. So your fixed point and eigenvalues is very important. So you need to know in each particular parameter that you use, you need to calculate your eigenvalues. So you can say what is happening in that particular point. Okay? And then after we have that analysis, then we can proceed with Lyapunov exponent. And the Lyapunov exponent will give us 3 analysis, positive, negative, and also 0. So basically, most of the time, chaotic system will have 0 Lyapunov exponent. Okay, basically. So, and then last but not least is bifurcation. Okay, so we have the flow in your mind already?
Yes, ma'am.
Okay, but then you are not trying for the, yeah, you are not trying. So how I want to give for the next one. So this one we not enough time to, we not have enough time to discuss this one in the lecture just now.
Maybe we can go up to 6 o'clock. Another 20 minutes you can do.
Yeah. Okay, so maybe we just touch. We have about 30 minutes, okay? So, yeah, you do the time series and the phase space for the Lorentz. Maybe you can try. You just change your equation and then you can see how, because I didn't give the result here, how the shapes of Lorentz, of Rosler. And then this is very important. So which parameter is actually primary
had?
When I 10 years old, I mean, after 10, we changing to the whiteboard.
White. As per the memory of the old.
Yes. Okay, so what is our fixed point?
You can use it.
So I think I want to have a picture with.
This one.
I like Dr. Sibarashi. Faster. Okay, so I'm acting just now. I want to take a picture. It has been a long time for me not to get the whiteboard. Sorry. Okay, so what's our fixed point?
C plus minus
C
plus minus
plus minus.
root under C square minus 4ab
So I'm so sorry.
under root C square
C square
minus 4ab
minus
Minus 4a.
4a square
AB
maybe
by 2.
By 2a.
divided by 2A.
मैंने कर दिया
2a.
हाँ कर दिया ऑन कर दिया
One, the other one?
Sorry, divided by 2
a
only.
नहीं होगा.
Divided by 2 only. In the second quadrant, third quadrant will same with divided by 8.
Be the same. C plus minus.
Divided by 2.
So minus. It will be minus plus
Over 2.
2A. Minus plus.
C
Third
with,
quadrant will also
C with minus.
C with minus. This one.
First one.
No, ma'am, minus C.
Oh, okay.
Yeah.
Alright.
And third one is
इसमें नहीं प्रैक्टिकल्स में
Okay. So
हाँ ये वाला होता है
so this is your fixed point.
हाँ हाँ कंबाइन कैलकुलेट के नॉट यूज
I get wrong.
X, Y, Z. Z coordinates.
Yeah. Sorry. I'm thinking I writing all already. So what is Z?
हैंड ब्रेक करके या इग्नोर
C
दीजिए
is second only. Like it will be a C.
Y
C minus plus. Minus plus.
Minus plus. particular fixed point, in this particular parameter, so which one
B.
is actually influence the stability?
हाँ हाँ ये अगला स्टार्ट हुआ था इधर यहाँ आपने रोका हाँ
Actually, B will
32 मिनट हाँ 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 ठीक है ओके ओके
Okay?
means that the previous solution will only be the solution of this system if B is 0.
Yes.
थोड़ी सा 30 सेकंड में
Yes. So if you substitute 0, 0, 0, so B will be 0. So that doesn't influence anything. So because B 0, so totally it's not influence. It's not. We will not influence the system at all. So the answer will be. Actually, the answer is A. Sorry. So the answer is A. Okay. So why? Because is actually directly in eigenvalues of Jacobian. Is actually if you are doing Jacobian, we can see. I think I have the Jacobian here. Yes, the Jacobian is 0, -1, -1, 1a, 0, z, 0, x minus c. So it will be directly in eigenvalues of Jacobian matrix. So a will affect the second eigenvalues, which corresponding to the linear growth or decay. So
36 5 को बोलना स्टार्ट किया
the value of a will affect the second eigenvalue. So that's why a plays important. I mean, give influence for the stability for 0, 0, 0. Okay. Again, because a when a will give direct what we call direct influence to the eigenvalues. So the second eigenvalues will change if we change the value of a. So in trivial, a give the influence of the stability. Okay. So how does parameter C influence the nature of the fixed point and their stability? I think you can see from the fixed point directly. The value of C is very important there. So maybe the one you already knows how to answer it. And also based on this term also, we can see it's directly play important role in the stability. Okay, yeah, because we are not doing this, so that's why, I mean, for you to check how we want to check the value of fixed point if you are not doing this. I mean, the value of, so, I mean, if you run it, then you have the value, the eigenvalue, so then we can talk about stability, right? So wait, let me see my okay, so yeah, I have it, the fixed point. So I'm using A 0.2, B 0.2, 5.7. Actually, I want my first purpose is actually I want you to get this one. That's why I didn't mention any of this parameter. So this is parameter whereby the system has a big chaos. Actually, in my thought, you will run the 3D and I mean the time series, so you can see what value will encounter the roster to be. I mean, to But then for each particular eigenvalues, if positive real part, complex positive real part indicates I just want
Stable.
unstable. Stable or unstable? I think unstable, right? Unstable. So positive unstable, negative will be stable. Okay? So negative will be stable. Okay? And then we have the second positive eigenvalues, and all are positive part. Right? All are positive part. But then this is actually chaos. So we don't need to talk about to talk about this one. So let's see if I'm changing the parameter. So because in Rosler parameter C plays important roles, so we change the parameter C to, let's say, 2. Okay? So you only have 2. If you put it 2, you only have 2 eigenvalues. One is the plus 1 and one is the fixed point, I mean the trivial. Why we don't have the minus 1? It's very obvious, right? Okay? So everything in the plus is positive real number, positive part. Okay? And the fixed point, we have 2 for positive and 1 negative. Will be that saddle there. Okay? So yeah, you can play around with the parameter C because it influences the stability. Okay? So as this one, the type of stability. Oh, okay. What is the type of stability just now? When we, I mean, 5.7, right? So what is the type of the stability for the question asks for the trivial, right? So for the trivial. So what is the type of the stability? What is the type of the fixed point? Saddle. Okay? It's a saddle. Alright, let's do it. Okay.
Are the ABC physical parameters or something else?
Again?
ABC are the physical parameters or something else?
Okay, yeah, actually for Rosler, yeah, it's supposed to be, I'm talking this one in the lecture right there. But then we have no time, yeah. So Rosler is actually, they are designed, they are modeled this equation just for the purpose to make it simplified from the Lorentz, and it doesn't have any physical implication. So it just want to show the simplified of chaotic system.
We can say they are artificial
Yes,
constants.
correct. Alright. And then, okay. But then my question is very obvious, right? So you know what is the answer for this? What is the physical or dynamical significance of a fixed point being classified as a saddle point? I think I'm giving the answer already in the lecture. That one is saddle point. That one is saddle point. So this one is saddle point.
One point is being stable, one is unstable.
So, yeah.
Stability and instability.
Yes, okay, yes. So what is the implication of this stable and unstable?
Like that will be oscillatory.
Will be diverge oscillation. Okay. I would say not diverge oscillation. It will be towards it's actually towards our topic, which is when we have the saddle points, our physical implementation, I mean the dynamical behavior is towards the chaos. So it's that's why I say it's very obvious, my question. So when we have the saddle point, means that our system towards the chaos behavior. Okay, so I think with that, that's all. Actually, I have one more question for Duffy oscillator, but then maybe yeah, you can mentioned for the nerve. So the transition between negative to positive as C increases. So what the transition signify?
System moving towards security.
My question is very obvious. I think I'm giving them a simple one, so I need to change my question for the exam. Okay? So this one also we already discussed. This is also already we already discussed. And so what role do the parameter A, B, C plays in the dynamic of Rosler? So for C they are giving the stability. For A and B basically they are not changing. They are not really changing. So parameter C is the most important for Rosler for the stability. Okay? And this is what I mentioned. I'm giving you the Duffing oscillator with this equation, but then I leave it for you to do maybe if you like to calculate this. And this is the parameter that the Duffing oscillator exhibit chaos. So maybe you can try, because Sivrasa mentioned I need also to pass this one. Okay, so I will just pass. Okay, so as a conclusion, we explore the chaotic system based on the time series, 3D phase, and then we check the level of exponent, we interpret the bifurcation diagram, and also the most important is we check the transition between the stability to chaos. And my mistake there. Okay, so chaos theory reveals the underlying patterns and interconnectedness in the system that appear unpredictable. So the application is so big. It can be in your daily life. It can be, if in my case I have studied the blood vessel in chaotics, and also basically more of it will be in cryptography. And now we extended to fractal, whereby we have the data set. So from the data set, how we want to check the behavior of the data. So we check the chaotic behavior there. So that is in my case. So also in cryptography, currently we are developing hardware whereby the real-time data, for example like a call or message, encrypted by my own algorithm. So because we want to use this hardware for military, because basically as I mentioned, I'm not in defense military, but then we are related to each other because we are giving them the officer. So we are interconnected. So I'm proposing to this hardware to use in military, but then I think it's very very difficult to get. But then that is what our invention. We are trying to make the invention. Maybe later on they can use my algorithm for the military service. So I think that's all for today. Any question?
You told that transient, we are removing transient for, so because here it will not show bifurcation diagram, right? It will not.
No, it just shows the temporary behavior. So that's why we don't bother. Actually I have a very good word for it. It's not don't bother, but then we can just I didn't get the term. We can just not to use the transient. So because it just shows the temporary behavior. Okay?
But it will not affect the data, right? Ultimately it will show the chaotic behavior, right?
No, it depends. I think you already asked, right? It depends. In Lorentz, no, there is no affected. So if you take, it doesn't affect anything. But then in Rosler, if you take
initial condition we are giving,
Yes.
ultimately it produces a chaotic behavior. So why are we leaving the first one written?
The temporary behavior maybe I don't know, but then it affected our plot. That's what I also not really. I mean I don't know how to mention in the physical application, but then it's affected the plot. That's what I always do. So when we remove the first transition, so they will be very good. But then if I didn't remove it, I didn't get what we want. So yeah, I know because we plot. I mean the parameter is there. The parameter is showing chaos in any initial condition. But then there is the problem with as I mentioned bifurcation. Sometimes it's quite difficult and we have to do some perturbation and everything. So there is I mean for us, if you have the chaotic system, the problem would be to get the bifurcation diagram. In fact, there is one paper I removed my bifurcation analysis because I didn't get the answer. But then yeah, definitely it's accepted because maybe I moved with another thing. Yeah, we make up. I removed the bifurcation, but then I make up with what we call 0-1 test. So 0-1 test, we can show the existence of chaos. So maybe that one justified and my paper is accepted. Okay?
Just 1 minute. Let us. Yeah. Like Professor Lamborghini is available today for asking any questions or any interactions or something, because tomorrow he will be busy. So if anyone would like to ask any questions or doubts, you can contact Professor Lamborghini. Do you have his phone number or email ID?
No, sir.
Phone number I am writing. You can message and you get his confirmation, and then you can meet him. He is available in the main guest house. In the discussion room. So you can message first whether he is available or not. Then you can. As he mentioned, there are a lot of students here. They ask some questions, doubts. So if you have any questions or doubts, you can ask his free time. Yeah, you can. I can also send.
Okay, sir.
Because some people may be not there in WhatsApp. But I'm saying.
Actually, down.
I mean, you are discussing more.
इसको day 3 का
I mean, this is
day 3 का
exactly
day 3 की मैं पहले कम डाटा ले लेता हूँ तो को डाटा ले लेता हूँ नहीं जान रखे हाँ खत्म